that if you have products in your simply typed lambda calculus, then, so the rules apply, so we're about to write down, then you have products in this category. So I just used the word product twice, but like products in the simply typed lambda calculus, I mean define the normal type theoretic rules, and by products in this category, I mean products in the sense I just defined here. Okay. Good to check that the two ways in which this word is being used actually coincide here. Okay, so talk about products in the simply typed lambda calculus. So we have always a formation rule. So if we have two types, A and B, then we have a new type, A times B. Maybe I'll actually start talking about the categorical interpretation at the same time. Okay, so we had 1 and we had 2. Okay, so if our type theory bold T has this first rule, then that definitely satisfies number 1 in the definition of product I'm giving here. And so I'm just going to show that products in the simply typed lambda calculus imply products in this sense in the syntactic category. Okay. So for any two types, for any two objects that are in the syntactic category, we definitely have a new type, a new object, that's number 1. Now, the introduction rule is not going to go exactly in order now. So the introduction rule says that if we have an A and a B, how did I fix this? Okay, so if we have an A and A, so maybe to be honest, in the simply typed lambda calculus, on this left-hand side of this rule, you might have a list of more than one hypothesis, more than one type here. But let's not simplify things for now. Especially since we're just showing that this implies this. So whether or not this can be a bit stronger doesn't matter. Okay, so if from some hypothesis said you can produce an A and a B, and of course you can produce something in A times B. And then we have the elimination rule. The elimination rule says that if you have something in, if you have something in A times B, which I'm calling P for pair, then you also have something in A, and you also have something in B. Okay, so now I want to say that this rule is giving us the pi A and the pi B. Can you see how? Yes.
Oh, for LS analysis.
Okay. So can you see how to get the morphisms pi A and pi B from this rule? Kind of similar to the answer that I gave about how to get pi A and pi B from the function that I had over there. And it's not kind of the same, it's literally the same. Yes?
That operation kind of corresponds to morphism, like the elimination rule kind of corresponds to those morphisms.
Yeah, so how do we get morphisms like this and like this? So here on the bottom, we have a morphism from a Z to an A that we get with these hypotheses. We have a morphism from a Z to an A, and a morphism from a Z to a B. But we need a morphism from A times B to A, and from A times B to B. So what should we do? Yes, are you raising your hand? Yeah. Exactly. We think about instantiating this, where Z is A times B. So I call it B again. Z is A times B. So some variable A times B, and then we're just using the identity morphism basically. So it's really, if you remember what I said about the getting pi A and pi B out of the common bijection definition, it's really exactly the same. So we plug in A times B for Z. We think about the identity here, or the variable rule, or whatever you want to call it. And then here, we get P and A times B, and P and A times B. That give us now these things. And this is exactly, by our definition of the category, this exactly gives us a morphism from A times B to A, and from A times B to P. That I might call, well, I might call it something like lambda P dot pi A P, but we will just abbreviate that as pi A. Okay, so a morphism here, pi A, and a morphism here, pi B. So, where should I write that? So here I get A to A times B, pi A, and, oops, that's wrong direction. I get A times B to A, that's pi A, and A times B to B, pi B. Okay. And now, I want to think about how do I get this U? And now I'll remind you that we picked something, the introduction rule. So how can I use the introduction rule to get the U? So the introduction rule tells us how to get something in or a morphism to A times B. And the U is a morphism to A times B. Right? It's actually a morphism from something arbitrary, just like its rule. Right? So the hypotheses correspond in the syntactic category to a morphism that here I call it little a basically. We have a little a in A, that's taking in this little g. So that's a morphism like this. Maybe I could have called it curly to be a little bit more clear. The other hypothesis is a morphism like this. Right? And it's saying that we get a morphism that's written as this pairing here, like this. So the pairing is the U. So it's exactly the pairing of this morphism. Okay, it doesn't say it's unique though, but maybe I'll kind of abbreviate things. That's almost noon. I haven't written down the computation rules, the beta and eta computation rules. But the beta and eta computation rules say very explicitly, if you just write them out carefully and slowly, they say very explicitly that this guy is unique, the unique thing that makes these two triangles commute, and in particular also makes these two triangles commute. So the beta and eta rules say that these two triangles commute, and that this guy is the unique guy that makes the two triangles commute. Maybe I'll leave that as an exercise. Okay, so to wrap up, today we have dot products and co-products. We've seen some more strategies on how to do things in category theory than before. Now we've defined a little bit more precisely the category of types that I talked about in the previous 2 days. The syntactic category. So the syntactic category of in particular, simply type lambda calculus is something like very concrete and specific, whereas before I said type and I meant something that was supposed to be this, but it was more vague. Okay, so now we've seen this specifically. And we've seen that the rules for products, so the simply type lambda calculus, give us, well, I just showed that they imply this stuff, but maybe you can also tell by the explanation that they're exactly the same amount of data. So the products in the simply type lambda calculus, or really in any type theory like Randall type theory, are the same as categorical products. Okay, so that's nice, of course, that we have these two concepts agreed. But why do we care about the syntactic category of a type theory? Well, it's maybe to prove things like the Curry, well, sometimes called the Curry-Howard correspondence, maybe I'll say the Curry-Howard-Lambek correspondence. So the Curry-Howard-Lambek correspondence tells us that simply typed lambda calculi, the category of simply typed lambda calculi, are equivalent to categories that have products and some other similar stuff. And so in particular, like those two things are the same, but maybe the most important part of that fact is that there's an interpretation of the simply typed lambda calculus into the category of sets. And that gives us the sanity check that when we're talking about stuff in the simply typed lambda calculus, we're talking about real stuff, let's say, as a real set theory is real stuff. Right? So there's some interpretation of this formal language, simply typed lambda calculus, in something concrete set theory. And in particular, like, then we are maybe feel confident that we're not doing something inconsistent when we're proving things in the simply type language calculus, and it maybe gives us some idea of what exactly we're talking about when we're talking about particular objects in the simply type language calculus. Okay, so we need an interpretation of the simply type language calculus in two sets. And how do we do that formally? Well, we produce a kind of morphism from the category, this syntactic category of the simply type language calculus into the category of sets. And this kind of morphism, so now I'm talking about morphism of categories between two categories. This morphism tells us exactly how to interpret all the types and all the terms. The objects are types and the morphisms are terms. So it tells us how to interpret all these constituents of the simply type language calculus into the world of set theory. Okay, so next time we're going to talk about what a morphism between categories is, called functor, and then we'll talk about this particular functor morphism. Okay, maybe, are there any quick questions? We have some time. Yes.
Are there like any useful non-thin versions of function? I think it's interesting or weird that pop is thin.
So the reason why pop is thin is because in normal logic settings, normal systems, they are proof irrelevant. So when you prove things, they don't care about how they're proved. They just care that like P and Q implies P. They don't care like why or how. So when we go proof relevant, then we exactly get the simply type language calculus. So the simply type language calculus is exactly like the non-thin version of natural definition. So it's the category, the non-thin version of the category prop. And indeed, the category prop is like a quotient of the category. Kind of, but not very well. Yeah, okay. Any other questions?